In this video, we're going to cover the structure and properties of acyl chlorides and acid anhydrides, and the acylation reactions undertaken by these molecules. We're also going to look at the nucleophilic addition-elimination mechanism, looking at the reactions of acyl chlorides with water, alcohols, ammonia, and primary amines. We'll then compare the use of acyl chlorides and acid anhydrides in use in chemical industry. Acyl chlorides, sometimes called acid chlorides, have the functional group COCl. It's analogous to a carboxylic acid, so you can notice it's very similar to a carboxylic acid. Apart from having an OH group, it has a Cl group instead. They're named in the same way as carboxylic acids, apart from the suffixes oil, chloride, as opposed to oic acid. The carbon in the functional group is always carbon 1, again, just like in carboxylic acids. So this molecule would be called 2-methyl-butanol chloride because it's got 4 carbons in the main chain with your acyl chloride functional group, so it's butanoyl chloride. There's a methyl group on carbon 2, therefore it's 2-methyl-butanol chloride. If you had 3 carbons in the chain, it would be propanyl chloride, 2 carbons, ethanol chloride, and so on. An acid anhydride is produced from 2 identical carboxylic acid molecules. The 2 molecules are linked through the oxygen on one of the OH groups, and we also produce water in the reaction. Here we can see the structure of the acid anhydride molecule. They are named from the carboxylic acid. We just replace the word acid with anhydride, and we'll look at an example of one of these. So in this case, we've reacted 2 molecules of ethanoic acid together, and this is our acid anhydride which we've formed. We can see we've essentially just joined 2 halves of the carboxylic acid together with a bridging oxygen in the middle. So there were 2 carbons in ethanoic acid, therefore there are 2 carbons either side of the oxygen in our anhydride. We used ethanoic acid to form this anhydride, so the anhydride will be called ethanoic anhydride. This is how we write the structural formula for an acid anhydride. As the acid anhydride has got 2 identical halves, we write the structural formula for one of those halves, put it in brackets with a 2, and then put the bridging oxygen on the end. We're now going to look at the reactions of acyl chlorides with a variety of different nucleophiles. In each reaction, the chlorine atom is substituted by the nucleophile. Each of these reactions will produce hydrochloric acid, which is formed as misty white fumes. We'll look at the mechanisms for these reactions in the second part of this video. We're going to start off by looking at the reaction of ethynyl chloride with water. When we react acyl chlorides with water, they will form carboxylic acids. So the reaction of ethynyl chloride with water would produce ethanoic acid and hydrochloric acid. You need to be able to write equations like this for any given acyl chloride with each of the 4 nucleophiles we're going to look at. When an acyl chloride reacts with an alcohol, it's going to form an ester. Just like if it was reacting with a carboxylic acid, the alcohol will join in exactly the same place. So for example, if we were reacting ethanol chloride with methanol, we would produce methyl ethanoate and hydrochloric acid. If you're unsure on how to name the ester or the process through which this reaction happens, have a look at the previous video looking at the formation and naming of esters. Acyl chlorides will react with ammonia to form amides. You'll study a whole topic about amines and amides, and in that topic we'll look at the naming and properties and the structure of amides and substituted amides in more detail. At the moment, just focus on what the product will look like. If you're not confident on naming these from this video, wait until you study that topic. So if we reacted ethanol chloride with ammonia, we would produce ethan amide and hydrochloric acid. So you can see here again how we've substituted the Cl group with the NH3 group, and it's formed NH2, and that's the structure of our amide. You can see how the extra hydrogen from the ammonia has reacted with that spare chlorine to form HCl. Acyl chlorides will react with primary amines to form N-substituted amides. Again, N-substituted amides can be quite complicated to name, so we'll look at those in more detail in the amines topic. So if we reacted ethanol chloride with methylamine, we'd produce N-methylethanamide and hydrochloric acid. Just focus on being able to draw the structure of the product. Acid anhydrides will undergo the exact same reaction as acyl chlorides, the only difference being that rather than forming hydrochloric acid, they're going to form a carboxylic acid instead. You can effectively think as everything here as being the chlorine atom from the acyl chloride, and the reactions will be identical. The chlorine atom on the acyl chlorides reacted with one of the hydrogens from the nucleophile to form hydrochloric acid. In this case, the whole part of this molecule here reacts with one of the hydrogens to form the carboxylic acid. In this case, it would be ethanoic acid, and we would join on whatever the nucleophile was to this part of the chain here. So all these reactions are analogous to those with the acyl chlorides, so you only effectively need to learn the set of reactions once. So for example, when acid anhydrides react with water, they're going to form carboxylic acids. Just like when acyl chlorides react with water, they also form carboxylic acids. In this case, given that the byproduct of a reaction of an acid anhydride is already a carboxylic acid, this is just the reverse process of forming the acid anhydrides, so ethanoic anhydride reacting with water would just produce 2 moles of ethanoic acid. Acid anhydrides will react with alcohols to form esters, just like acyl chlorides react with alcohols to form esters. So in this reaction, ethanoic anhydride will react with methanol to produce methyl ethanoate and ethanoic acid. Acid anhydrides will react with ammonia to form amides. So ethanoic anhydride will react with ammonia to produce ethanamide and ethanoic acid. Finally, acid anhydrides will react with primary amines to form N-substituted amides. So ethanoic acid will react with methylamine to produce N-methylethanamide and ethanoic acid. Naming the N-substituted amide isn't important at this part, but just seeing how we can add on this part of the molecule to the acid anhydride. We're now going to look at the mechanism through which these reactions take place. We only need to outline the mechanism of the nucleophilic addition-elimination reaction of acyl chlorides with water, alcohols, ammonia and primary amines. We don't need to draw the mechanism, and we're not going to learn the mechanism for the reaction of acid anhydrides. As each of them will produce the same products, you can still use this to help you figure out what would be produced if an acid anhydride was to react, but we only need to draw these mechanisms for acyl chlorides. We'll now look at the general mechanism. So like we've just looked at, the acyl chloride will react with a nucleophile to produce whatever our product is, where the nucleophile has substituted the chlorine atom, and will produce hydrochloric acid. As we mentioned in the earlier part of the video, effectively one of the hydrogens from the nucleophile is going to be lost, which will help reform the hydrochloric acid at the end. It will help us when we draw the mechanism if we include the trailing H from the nucleophile, so we'll look at how to draw these in each of the cases for the specific nucleophile. It's just going to prevent you losing that hydrogen in the mechanism, because it does play a part in it towards the end. So the first step is to draw out the nucleophile with the trailing H and the acyl chloride. The first step of the mechanism involves two curly arrows. The lone pair on the nucleophile will attack the slightly positive carbon, forming a bond with the carbon. The carbon will be slightly positive because it's going to have a slightly negative oxygen here and a slightly negative chlorine here. As the electrons move from the nucleophile to the carbon, a pair of electrons from the carbon-oxygen double bond is pushed up onto the oxygen. The result of that step is we've now made a bond between the nucleophile and the carbon. As the nucleophile has now formed an additional bond, it has a positive charge, and we're still showing that trailing H. As we've broken one of the double bonds and those electrons have moved up onto the oxygen now has a negative charge. The next step of the mechanism is for the lone pair on the oxygen, as it's had the electrons moved up to it in the first step, then reforms that double bond. The electrons are pushed onto the chlorine, breaking the CCl bond. The final part of the mechanism is going to be to remove the trailing H here, to remove the positive charge on the nucleophile. And we do this by drawing an arrow from the nucleophile hydrogen bond up to the nucleophile. This will give us our final product. We'll now look at worked examples for the reactions of various acyl chlorides with water, alcohols, ammonia, and primary amines. To start off with, we'll look at the reaction of ethanol chloride with water. We're going to draw the water out like this. It's important that we show at least one of the H's in the reaction, because it'll make it easier to draw the mechanism so we don't get our intermediate structure drawn incorrectly. As water only has two H's, this is the simplest way to draw it for the mechanism. The first step, like we just looked at in the worked example, is we're going to draw the lone pair on the oxygen. We're going to have an arrow going from the lone pair on the oxygen to the carbon, and then break the carbon-oxygen double bond. This will give us an intermediate structure with a new bond between the oxygen and the carbon, giving the oxygen a positive charge, and a negative charge on the oxygen up here, because we've broken that double bond with the electrons moving up to the oxygen. The next step is to reform the oxygen double bond by drawing the lone pair on the oxygen. Having that lone pair with an arrow coming down, this will reform the bond, breaking the carbon-chlorine bond in the process. This gives us our final intermediate structure, and we can see the carboxylic acid we're going to produce starting to take shape. The oxygen still has a positive charge, so we'll need to lose one of the hydrogens to remove that positive charge. And we'll do that by drawing an arrow from one of the hydrogens, so from the OH bond, back to the oxygen. And that will give us our final product of a carboxylic acid. If we react an acyl chloride with an alcohol, we're going to produce an ester. Again, we're going to be really careful to draw our nucleophile to show the molecule which is going to do the attacking below the acyl chloride. We're going to make sure we've drawn a trailing H, and the remainder of the molecule can just be coming off the side like this. We're going to draw the lone pair on the oxygen, an arrow coming from the lone pair up to the carbon. We're then going to break the carbon-oxygen double bond by having the arrow go from one of those double bonds up to the oxygen. This will give us that intermediate structure we're becoming familiar with. with a new bond between our nucleophile and the carbon, a positive charge on the atom which did the attacking, and a negative charge on the oxygen at the top as we've broken that carbon-oxygen double bond. We'll then draw the arrows from the lone pair on the oxygen, reforming the double bond and removing the chlorine. This gives us our final intermediate structure. Again, we can see the ester taking shape. We're just going to need to remove the hydrogen to remove the positive charge in the water. We do that as we've done previously by drawing an arrow from the OH bond to the oxygen. When you react an acyl chloride with ammonia, you'll form an amine. As always, we're going to make sure our nucleophile has got one trailing H. You can see how this makes the final step of the mechanism where we've got to remove that H much easier. We don't need to draw the other two H's fully displayed if you don't want to. This is a perfectly acceptable way to draw the ammonia nucleophile for this reaction. The mechanism should be becoming quite familiar to you now, so we're going to draw the lone pair on the nitrogen atom, have a curly arrow going from that lone pair up to the carbon, and then break the carbon-oxygen double bond. This should give us, again, our familiar intermediate structure with a negative charge on the oxygen and a positive charge on the nitrogen. We'll then draw the lone pair on the oxygen, show that lone pair coming down and reforming the double bond, and removing the chlorine in the process. Our final intermediate structure will show pretty much the amide, but with the additional H we need to remove. Again, this is why drawing the H in this way from the start of the mechanism will make this step much easier to spot and make us less likely to make a mistake. We then remove the H by drawing a curly arrow from the NH bond to the nitrogen. When we react an acyl chloride with a primary amine, we're going to form an N-substituted amide. As before, we'll draw our primary amine showing the trailing H. In this case, it's easy to show both of them like this so we don't make a mistake in writing the formula for the molecule. We'll draw the lone pair on the nitrogen, show a curly arrow going from the lone pair to the carbon, and then break the carbon-oxygen double bond. We'll then draw our familiar intermediate structure with a negative charge on the oxygen and a positive charge on the nucleophile, in this case on the nitrogen. The next set of arrows show the lone pair on the oxygen, forming the double bond again, so through this curly arrow here, and removing the chlorine. Giving us our final intermediate structure with one of the H's which need to be removed. Through the curly arrow, drawn a couple of times now, making sure it goes from the bond to the nitrogen. We're now going to compare the uses of acyl chlorides and acid anhydrides in chemical industry. So through a variety of reactions, through all the ones we've looked at in this video so far, so for forming esters for example, you've got a choice of whether you want to use an acyl chloride or an acid anhydride. We're going to look at the advantages and disadvantages of using both of these. Acyl chlorides are very reactive, which is an advantage for them, means your reaction is probably going to go a bit quicker and more to completion. However, acid anhydrides are less reactive than acyl chlorides, so that'll be a disadvantage for them. Acyl chlorides, however, are a corrosive chemical, so they need a lot of care when they are being handled and used in the lab. Acids anhydrides are less corrosive, so they are a bit safer to use in the lab. When you're giving answers in an exam question, make sure you comment on how corrosive they are as opposed to how safe they are to use. It's much better to use that kind of terminology rather than being generic with safer. Explain why they are safer or less safe, and that is to do with how corrosive they are. Acyl chlorides produce harmful products. They produce those misty white fumes of hydrochloric acid. These can be especially harmful because while you may use hydrochloric acid in its aqueous form, that's quite easy to contain as essentially a liquid in a beaker. If you produce vapours or fumes of hydrochloric acid, they can be quite easily inhaled, where those hydrochloric acid fumes will then dissolve into the tissue of your lungs, forming the aqueous hydrochloric acid inside of your lungs, which can give you quite nasty chemical burns. It's for one of the reasons that we don't actually use acyl chlorides during A-level practicals, because it can be quite a harmful and dangerous chemical to use. Acid anhydrides produce much safer byproducts, so we know they produce carboxylic acids, which are a lot easier and safer to handle than the hydrochloric acid fumes. Acyl chlorides are more expensive than acid anhydrides, which is a disadvantage. So acid anhydrides are obviously cheaper. You'll have to weigh up these factors based on the information given in a question and evaluate which might be best for a certain use.